I'm down today.
No.
The 6.1 quiz will be up after school today. 6.1 homework key is posted. The 6.2 homework and homework key is posted. I think that's it for scheduling. Questions on that?
No.
Okay. Questions on 6.1 problems that you have questions about? About which you have questions, I guess, to be grammatically correct. Nothing? You guys are good on 6.1? It was relatively straightforward. Okay. Guys, reminder, two things that we talked about yesterday. First off, definite integral. Thing one, it's the area under the curve. Thing two, it's the limit of a Riemann sum as the number of rectangles goes to infinity. And thing three, the notation is that the limit of this Riemann sum can be written as the integral from some low point to some high point of the function differentiated with respect to small slices of x. Okay. That was the gist of yesterday. That's what we talked about yesterday. And then we did examples. And of course, remembering that this is an area. Going back and looping right back to number one on that list. So what I want to do today is we're just going to do some more specific examples. And let's talk about a constant function. So let's assume that f of x is a constant. And we're looking at the interval a to b. Graphically, this is the problem that we started with in 6.1. We've got some function that is a constant. We're going on the integral from a to b. And therefore, the integral from a to b of this constant value, do I want to write f of x or do I want to write c? I want to write f of x, is equal to the integral from a to b of the constant. But looking at the area here, the height of that rectangle is c, the base of the rectangle is b minus a, which means that this integral is equal to c times b minus a. Does that make sense from just a physical standpoint? Velocity of our ship was constant. And we said, oh, well, the area under the curve will be the velocity times the change in time across the bottom of our graph. So what does that tell us? Well, it just tells us that we now have a rule. For a constant function, we can just take the constant, take the difference between the upper and lower limit and multiply them together, and we've got the value of the integral. We've got the value of the area under that curve, and we don't have to think about it anymore. Right? And we're going to use this fact down the road. So why don't you guys go ahead and do exercise 29 out of the book. Don't forget we're at 6.2. What last year? I don't post them, they just pop up automatically.
Okay, then that makes more sense because I didn't see it till like this morning.
Sometimes I just take a lot.
If I don't know, we'll give you the video.
Yeah, no, that's,
Cause I looked at for like last night when I was like, wasn't there. And then I just looked down and.
which is odd. And I have no control whatsoever. I mean, I do them and then I click stop, and then I thought they were supposed to be there automatically, but maybe they have to process before they pop up as a recording, and that depends on YouTube. So yes, so it's there now. Sorry about that.
It's okay, so I don't know what to do right now.
Okay.
I'm gonna. That's wrong.
Did you write down those three things?
Oh, no, you erased
didn't?
it
I
right
erased it too
before.
fast? Okay, here we go.
Thank you. I was like, okay.
Here's what we did is we said, if we take some curve and we want to know the area under it, we can split it into lots of little rectangles and add them all up. We said that this was the sum of all the rectangles, where the function is the height of the rectangle and delta x is the width of the rectangle. The more rectangles we have, the more accurate it is. Then we said that, well, there's this new thing called an integral, and an integral is defined as the limit, because our rectangles go to 0. So in other words, we're gonna have like an infinite number of really skinny rectangles, and we're gonna add up all those. So that's sum. And then we said there's new notation, and instead of writing the limit of the sum every time, we write that, which means the limit of the sum. And then the interval AB, we start at A, we go to B. So this is the sum from A to B of all the rectangles. And then we stick the function right in here. And we put the dx to say, yeah, because we're talking about the x direction. That's the gist of it.
Okay. Thank you.
And we'll go into more detail on the video with examples and everything.
Mhm.
All right, exercise 29, did we do it? Are we happy? Did the answer make sense? All right, I have no idea what the question is, or what the answer was. Very easy.
It's like a fifth grade question. Probably third. Okay, for you.
Find the distance traveled by a train moving at 87 miles an hour for 3 hours. Oh, yeah. What do trains travel at 87 miles an hour? All right, doesn't matter. Generally not 87 miles an hour. I guess it depends on the train too.
This could be China.
Yeah, it could be in China, running their high-speed train between their empty cities with nobody on them. All right, we're gonna change up our notation a little bit. Because we said the integral from a to b of f of x dx is the area under the curve f of x from a to b. But what if I want to find the area under the curve at some value? Because I don't want to go all the way to b. I want to know what's going on in between. I want to know, for example, how much snow there is at any time t. Instead of how much snow is there at 10:30 when the snow stops. We talked about that snowfall problem the other day. We said it starts at 3 and it does this and then it does that and then it does this and it stops at 10:30, and at 10:30 we knew we had X amount of snow or some certain amount of snow. Well, what if I want to know how much snow there is at 4 or 4:30 or 5? So the notation that we're looking at right now, the idea of this accumulator function we say that S of t, the amount of snow at time t, notice this is a capital T, and that makes a difference, is equal to the integral from 3 to whatever time we're talking about of the rate that snow is falling dt, lowercase t. The function r of t tells you how fast the snow is falling at any given time. Capital T tells you what time you're interested in. So that's the b. Where am I ending if I want to know how much snow has fallen? All right? These have to match. And that should be different. You don't want to put a little lowercase t there because then you're just saying, well, then those are the same thing, and then it messes you all up. Now, I'm making a big deal out of this because I remember when I took calculus, this just confused me no end. There were just like different variables left and right, and I don't even remember whether any of my calculus professors even mentioned it. They just sort of said, yeah, okay, so at time t, blah, 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 and off they went. And they didn't stop and make a deal out of it. And so for ages, I was just so confused because all the different letters were everywhere. And so I thought, okay, when I teach calculus, I didn't think that back then because I had no interest in being a math teacher. If I was going to be a teacher, I was actually going to be a history teacher way back then. But I wasn't going to be a history teacher either because I was getting a degree in engineering. Hey, believe me, you don't have to decide what you're going to be when you grow up, ever. So when we look at this, what we're saying is that snow started falling at 3 o'clock and it stopped at 10:30. And that number is somewhere between when it started and when it stopped. And it allows me to, instead of just saying, well, how much snow fell, to be able to say, well, okay, the snowplow went through at 8 o'clock. How much snow was there when the snowfall went through, or when the snowplow went through? Oh, okay, well, after the snowplow went through, then this happened or that happened. And now you can actually do calculations instead of just say, well, okay, we've got this big old thing to tell us how much snow there was. We didn't need this to tell us how much snow there was. We looked at the graph and we said, well, look, there's the graph. Or we went out and we stuck a measuring stick in the ground and said, well, look, hey, there's 8 inches of snow. We didn't need all this, but this allows us to do calculations as we go along. So what does this look like more generally? More generally as an area function, because an accumulator is just an area, any area function. I mentioned to you guys yesterday that I don't like the fact that they only use accumulator for things like snowfall and not for velocity or distance rather. Why can't you accumulate distance? Of course you can accumulate distance. So why distinguish? But generally what we say is that some area at x is equal to the integral from a to x of that function. This is on the interval AB, and x has to be between a and b. Notice that my input variable becomes what time am I talking about, or I can't think of an example off the top of my head that isn't what time am I talking about. Good morning. Yes, clock's working today.
It was more fun yesterday.
It was. Yesterday, you guys didn't see it because it was after, but I put a piece of paper up there and I would just climb up on a chair every 5 minutes and write the time in red pen and then cross it off 5 minutes later and write the new time because my kids were working on a project in Algebra 2 and I wanted them to know what time it was.
Are we integrating?
We are introducing integrals.
Nice.
Yes, with a week and a half left, so that's awesome. But I figure they'll get to college and
They'll have seen it.
they'll have seen it and it'll make some more sense. So what we were just saying, let me recap what we were just saying, is that this is my input. This is the number that I'm interested in. This is when I care about. This is 4 o'clock or 5 o'clock or 8:15 or some time between A and B. And this is the function here that tells me how to find my area. I'm going to start here and I'm going to end at some variable time. Questions? Example. We've got a function f of t equals 1 plus 2t over the interval 1 to 6. And I want to know the area underneath that function for any value of x. Now, notice that I'm starting at 1. I'm starting at the left side because it's an accumulator. I'm starting at the very beginning. A very good place to start. Yeah, now you're all singing in your head. And I'm working my way to the right. What?
What song?
Sound of Music? Let's start at the very beginning. Very good place to start. When you read, you begin with A, B, C. When you sing, you begin with Do, Re, Mi. You guys haven't seen The Sound of Music? You just don't remember the song? You need to all go watch The Sound of Music again because it is a great movie. Like, not just I enjoyed it and it's fun, it is a great movie. It is one of the all-time classics. But yes, that's the song where she's teaching them how to sing. And so the do, re, mi is the scale, and she introduces it that way. Okay, so anyway, we're starting at 1, and we're adding stuff as we move to the right. We're adding area. So A of x is the area under the graph at x. Area under graph at x, or up till x. So let's see what this looks like. Well, linear function, 1 plus 2t, starts there. Here's A, and here's x. Do we agree that this has a height of 3, since that's the graph of 1 plus 2t? Okay. And this has a height of 1 plus 2x. And this is x minus 1. Area of a trapezoid?
Oh, yeah, that's a weird one.
Here's how I remember it. Here's my trapezoid. And if I spin it around and I put, another identical trapezoid upside down, I get a parallelogram. And the area of a parallelogram is the same as a rectangle, which means that the trapezoid must be divided by 2, and the base has to be one of those plus one of those,
Well, that's good.
where this is base 2. So then all I have to remember is that, oh yeah, I'm just making a parallelogram, adding those together, multiplying by the height, and then dividing by 2 because there's 2 of them. So base 1 plus base 2 divided by 2. Well, there's base 1 because my trapezoid's turned on its side. 1 plus 2x plus base 2 divided by 2 times the height, which is x minus 1. Let's do some simplifying. I get 4 plus 2x over 2. I get 2 plus x, agreed? Times x minus 1. The area from 1 to x underneath the function 1 plus 2t with respect to time is x squared plus x minus 2. Now you can find the area under that curve, because rather than just here's some numbers, find the area, you can find the area under that curve for any value of x up to 6. Because we're told that whatever it is we're talking about right here is linear with that particular function between times 1 and 6. So I want to know what's happening when x is 2. I just plug in a 2. 4, 5, 6, 5, 4. The area from 1 to 2 is 4. Plug in x equals 5. The area from 1 to 5, 25, 30, 28. I've got a formula for area under that curve. If I start at 1 and I go up, and we're told this is valid all the way to 6. Questions? Cool. Why don't you guys do exercise 33? Ethan?
3 x minus.
Constant rule, constant function, so we didn't really even have to draw the picture of this one because this is just a horizontal line. Had we drawn the picture, we would have said, there's my function. There's my base, there's my height. So this is what they mean when they say write as a polynomial. They just mean write it like that, or write it like that. All right. Questions? All right. What if I want to do it with my calculator? Because why wouldn't I? Yeah, it's graphing calculator. No, you know what? Shoot, I wanted to leave that. Okay, I'm gonna leave that. I'm gonna drizzle down.
Wait, integral is a real word?
Integrable?
I thought you were just joking and said you like made that up.
I never joke or make stuff up.
Oh,
Where do you get these things?
Gosh.
Everybody push the math button on your calculator. Everybody scroll down to number 9. I believe it says FNINT on your calculators. Press number 9 or just hit enter on that one. And it will give you this on your screen. No, it won't. Yes?
Yep.
Well, we already said from 1 to 5 would be 28 because it's 5 squared plus 5 is 30 minus 2 is 28. So let's type in 1 to 5 of 1 plus 2x dx. Now, be a little bit careful. Remember, we've only got one variable in our calculator, so we're going to have to change that to x no matter what. Unfortunately. Let's see if that says 28.
Yep.
Oh, Curtis, ruin the surprise for everybody else.
Oh, sorry.
Wow. And here they hadn't even finished typing, and now you've ruined it.
What do you mean? I'm sure they have. I'm red-handed.
What's that, Ethan? You were just helping me mock Curtis?
No, I was just thinking.
Oh, okay. Okay. So if I want to calculate a derivative, a definite integral, I can just put it right in there. Now, if I go to my screen and I put x, what do you think happens? Everybody go and put x in there instead of 5. Go math 9, but go 1 to x of 1 plus 2x dx. What do you get?
Whatever value you have set for x. So,
What value did you set for x, Curtis?
oh no, you have to put a 10. Or something.
Well, I didn't want you to put a 10. I wanted you to put an x.
No, I did.
Oh, okay. Neela, what answer did you get?
4.51.
Claire, what answer did you get?
-2.115.
Teresa?
21.76.
Curtis?
30.8125.
Ethan?
I got the same thing as Teresa.
Weird.
Awesome.
Interesting. Turnberg?
Same thing as
Interesting. And Teresa then by extension? Oh, okay, just checking. Let's see, what's that, the commutative property? If Teresa equals Ethan and Ethan equals Turnberg, then Teresa equals Turnberg. right? Hey,
What's your X at?
here's one. Everybody just put X and then hit enter. Hey, Andrew. Everybody just type an X onto your screen and then hit enter. What?
I have negative 0.8666.
I have 2.1.
So here's where that comes from. Just the last time you did a calculation using a program that involved an X, it had stored something in that memory register. X is a memory register in your calculator. There's a memory register for every single letter of the alphabet. If you go A, enter, it will give you a number probably. And it will probably be the last time you did quadratic formula program because you entered A equals. And it stored it in there. So this is why you got to be really, really careful about putting X onto into formulas in your main screen. This is why we never do it. This is why we never write or type in 1 plus 2x as a linear function into the main screen, because it's just going to go to the memory and pull out whatever x was last time you used it for something and tell you what it's equal to. And it will be meaningless unless you specifically stored a number at x in order to use in your next calculation. All right? So that's how you do it in your calculator. Okay. Next, what might we want to do? We might want to graph the integral. We might want to graph the area under the curve. So let's do this. I want you to go into y1 and I want you to type in 1 plus 2x. And I want you to go into y2 and I want you to type in the integral. Don't know if you saw that, Andrew. Math menu number 9.
Thank you for pointing that out.
From 1 to x of y1 dx. And I want you to graph them on the same screen in a window from 0 to 10. And 0 to, say, 25. So go into window and change your window to this. Because this is where we care. We only care about 1 to 6. There's your original function. What does your area curve look like?
How do you do the Y1 thing?
Alpha F4. So alpha trace.
Wait, what? Oh, yes, alpha F4 is the easy way, or the VARS key.
Yeah.
VARS, but the alpha one's easier. And what should that derivative look like? What should the derivative look like? Yeah, it should look like a quadratic, right?
Yeah.
Because we already know what it looks like because we figured it out earlier. What's it equal to when x is 1? One squared plus 1 minus 2. Does it make sense that the derivative, or I keep saying the derivative, that the integral from 1 to 1 would be 0? How many rectangles do we have between 1 and 1? We don't have any rectangles. As we just actually discovered another property of integrals. which is that the integral from a to a of some function is 0. Just because we're not counting any rectangles. Agreed? Approximately. Since I don't have a graph in front of me. And I'm not interested enough in what it actually looks like to go look at it. Okay. So we can calculate an integral, a definite integral, using Math 9. By the way, you guys all know that when you go to the math menu, you can just push the number 9 on your keyboard and it will pull up that one. As you use these more and as you get used to them, you start to know what numbers are various different things, and it really speeds up the process. If you can just hit Math 8 for derivative, Math 9 for an integral, you don't have to scroll down every time to find it. So those are the kinds of things that if you pay attention to them, they start to embed themselves in your memory, and then it's super easy to get there. And we can graph the integral by just going from a to x instead of from a to b. This is going to have to be from a to b, but we can graph it by going from a to x. Now, notice again, like I said before, you got an x here. Ooh, have your calculator out in front of you. Example number 1. The integral from -1 to +2 of x sine of x dx. Calculate. Neela, 3 decimals?
Oh, I only wrote down 2.
Oh, Neela,
I'm sorry.
you should be.
2.042. I'm sorry. Or can
Anybody get a different number?
I can round it up if you want.
You got a different number, Claire? What'd you get?
I got 0.052.
3 decimals, Claire. 3 decimals.
That was 3.
No, that's 2 decimals. That one doesn't count. It's a placeholder.
That count?
That's a placeholder.
Okay.
Significant decimals is the ones that, because otherwise, if I said round that to 3, if I said round that to 3 decimal places, what would you write? If those ones count, you'd have to say, well, it's equal to 0, which it clearly isn't equal to 0. Does that make sense?
Okay, yeah. And then there's a 3. Wait, there's a 4.
Why do we have 2 different answers for the same problem? Is that possible?
I got 2 points.
Is this just a non-function? The area under the curve of x sine x isn't even a function, so there are lots of different possibilities. Anybody? What about that equation requires us to do a little bit of advanced planning?
The x before the sine x.
Nope. Nope. Narrowing it down, running out of things. What requires advanced planning in that expression right there? Nobody? Really? So Curtis is going to say the X, and I'm going to say no. And Claire's going to say the domain, and I'm going to say no. And you guys can't think of anything else that might be up there that could cause a problem.
The sine function.
What about the sine function?
I don't know.
Because there we go. Thanks a lot.
negatives and positives.
Oh, well, how come they canceled out for Claire but not for Neela?
That'll be a better calculator.
Wrong mode.
What mode do we have to worry about when we're dealing with sine, Ethan? Radians versus degrees. Yes. Which one do we need to be in?
Radians.
We need to be in radians. Radians.
Get out of here.
Radians is the default for everything.
I got it right.
Hey, guys, you remember when we were taking the derivative of sine and we said it's got to be in radians, and then we showed, so if I took the derivative of sine theta in radians, I got cosine theta. If I took the derivative of sine theta, but I converted it into degrees, then the chain rule said that the derivative was that. Right? Remember that? Radians is always the default in real life.
But then,
And degrees requires a conversion factor.
were we using it for degrees specifically?
No.
I don't know. You may have.
Okay.
What do you do for fun on the weekends? I don't know. I go crazy on the weekends. I go downtown and I calculate trig functions in degrees with my graphing calculator. It really bugs people walking down railroad.
That was accurate.
All right, good. Well, I'm glad that came up because the more times I can reinforce little things like don't forget to put your calculator in radians, the better.
Glad we could figure it out so quick.
I was one step ahead, I mean.
Go. Degrees or radians on this one?
I feel like I've seen this before.
Where do you recognize 1 over 1 plus x squared from? It's a derivative. Tangent. Or, excuse me, arctangent. Derivative of tangent secant squared. The derivative of arctangent, remember, I think it was 1 over 1 plus x squared. I don't usually memorize those. I look them up when I need them. What do you get, Claire? Do we agree? Cool. How about integral from 0 to 5 of e to the negative x squared dx? Go. Andrew?
I got 0.886.
Do you agree? You guys know how to make a fraction in your calculator?
Yeah.
You can do this. You guys know the other one?
Alpha y equals.
Yeah. Alpha y1, or f1 rather, will give you the option of n over d. So you can type fractions directly in. The only downside to this is that if you type in a function into y equals, and then you make a table, guess what your table will be? all fractions, which can be super annoying when you're trying to do something. Yeah, it's it's stupid. I don't even know why they do that. It's like, why not give the option or something? Say, no, I want my table to be in the decimals. What the heck? So
Yeah, we should take that. That's a good calculus project that your project is just make.
We found, Washington Instruments.
here's the problem that you would run into. Texas Instruments is big enough to give away tons and tons of free lesson plans and free software and discounted calculators to schools and school districts, basically on the grounds that, and everybody, oh, you want to use ours because we've got all this stuff. Like you can go online and there's like whole books that they'll just give you as a teacher for lesson plans using graphing calculators. And it's a brilliant marketing scheme. They just say, well, let's get everybody used to using TI calculators. And what will they do when they go to college? They'll have a TI calculator. And what will they do when they become an engineer? They'll have their TI calculator and they'll shove it in their pocket and they'll go be an engineer. And meanwhile, Hewlett Packard, which is the other big calculator brand, I bet you guys didn't know that. HP, like the people that make the computers and the printers. Yeah. HP calculators, though. Okay, aside. Reverse Polish notation. RPN. Let me tell you about RPN. It's awesome. 3 plus 4 times 5 squared minus 6. If you were going to do that in your calculator, you have to type all of that in just like that. Agreed? Here's how you do it in an RPN calculator. Now you got 4 in your memory. Now it gives you 20. Now it gives you 23. Now, I might have that wrong. It might be this. Now it squares that number. Now it subtracts 6. The nice thing about it is you never get the parentheses wrong as you're typing out a really long, complicated equation. You just start in the middle and you work your way out. Now, what if you wanted to do this? You would type 3, enter, 5 plus squared. I remember now, there's no sign for making the power, you just hit the squared button. Which means that there probably is for this one, so it's going to be awkward. Now you've got that number. Next thing I do is I hit 6, enter, 7 plus cubed, and then I hit the minus button, and it takes that away from that. And then I go to the last one, and I hit 8, enter, 1 plus, however you do the 5th power, and then I hit the plus button, and it adds this to my previous result. It always keeps your previous results in memory, so you can just keep working your way through and just tacking them on to whatever it is you need to do. And it could be multiplied, it could be divided, doesn't matter. You calculate that. If this was a divided, then when you calculated that, and then you calculate this, as soon as you hit enter, it starts over again and starts calculating the next thing, but that's still sitting in memory. And so when you get to the end of this one and you hit divide, it says, oh, you want to divide this into the previous thing that you did. Yes, I do. They're insanely powerful for long, complicated equations. And meanwhile, people on their TI-84 calculators trying to keep track of parentheses after parentheses after, if you have multiple stacks of parentheses because you're doing some complicated engineering thing, and you're trying to keep track and you miss a parentheses and then it just gives you an error, and then you got to go up, hit enter on your equation, bring it down, and then start scrolling back and forth on your screen trying to figure out where you missed the parentheses. And I mean, this I got my first HP 41CV in college, and it wasn't a graphing calculator. It says I still have it. I still use it all the time. It's in my desk at home. I use it anytime I'm just calculating, doing my taxes or just whatever. And I got good at this at college. And I'll tell you what, you put up somebody who's good at RPM versus somebody who's good at just typing equations into your TI calculator side by side and give them a page of calculations to do. The guy with the RPM will have finished and gone down to Bob's to get lunch and be back before the other guy finishes. It is amazing. They are amazingly powerful. And nobody hardly ever uses them because it's confusing when you first start explaining it. When you first say, here's how you calculate 3 plus 5. Well, why wouldn't you type 3 plus 5 equals? No, it's 3, enter, 5 plus. People are like, oh, I don't get that at all. It's so confusing. But yeah, amazingly powerful. They're awesome. All right, there was an aside.
Our hour calculator is forward Polish notation.
What's that?
Our hour calculator is forward Polish notation.
No, it's just forward notation. I don't know if there's any particular ethnicity or nationality attached to that. And honestly, I probably knew at one point why it was called reverse Polish. Probably just based on the people that came up with the calculational, whoever it was that came up with the calculational system. Couldn't tell you there. All right, guys, let's talk about the difference between functions and accumulators when we're looking at a graph. I want you to graph two things. And I want you to look at the graph, and I want you to tell me how you know which is which. And look for multiple ways to think about it. If you can come up with multiple answers to the question, how do you tell which is which, that would be even better.
Should our window be like normal?
Well, your window in the X direction only needs to start at 0 and go up because we're not interested in what happens to the left. This is one of those where a quick analysis, what's the maximum value of cosine? One.
Yeah, okay.
Think about the unit circle, right? Minimum value of cosine? -1. So whatever value of x we're taking, it's x plus cosine is going to cycle around positive x, negative x, which means that this function should theoretically oscillate, agreed? So when we're looking at the function, it's one of those things that if we have x go from 0 to 10 on our graph, well, really that means that we only need to go up to what, maybe 15 and -15, because we're adding 1 and then oscillating. Guys, this is a general thought process. Whenever you're thinking about a function, before you start diving into your calculator, start by thinking about what you know about the function. Because randomly plotting through your calculator, poking buttons and hoping something interesting happens, isn't a great way to get a math problem done. It's sort of like plugging in the one with the sine. First thing you should be thinking is, oh, what do I know about trig functions? Oh, I know there's radians and degrees. Oops, I better double check before I go typing. Same thing with this one. What do I know about 1 plus x cosine x? You could just do a random big graph and then look at it. But the problem is you've got an oscillating function. Well, what if you go too far in the y direction? What are you going to see in the oscillating function? You're going to see, you might not even see any oscillations. And depending on where you are in the x direction, if you're at 100 and this is 5, you're not probably going to see anything on your graph because it hasn't oscillated high enough to show up on a scale that goes from negative 100 to 200. So these are important things. Before you start doing an actual math problem, it's important to just sort of sit down and think for a second. What am I expecting here? Okay, now I can plan. Tarnbeer, how did you tell which was which? Which graph was which on your calculator?
The cosine one loaded first. Yeah.
Oh dear. Oh
And it
dear.
loaded faster too.
I am reminded of the algebra student who you say, what's the difference between those two? And they say, well, one of them has a 2 and one of them has a 3.
You said any way to tell is a good.
I expect better. I really expect better from you guys. Hey, Turnbeer, other than the fact that one came first and the other came second, any thoughts?
I'm guessing the first one oscillates, but the second one doesn't oscillate.
So, do we know that the second one's not going to oscillate? I mean, if the first one's oscillating, doesn't that mean at some point we're going to have negative areas? Because every time that x cosine x dips below the x-axis, my graph's going to start going back down again. And then it gets above the x-axis and my graph's going to start, and it's going to keep doing that. So I'm going to have some oscillation. But honestly, at this point, I have no idea what that second graph is going to look like. Ethan.
Well, the top one starts at 0, 1.
And the bottom one starts at?
0, 0.
Has to, doesn't it? Because the integral from 0 to 0 is 0. So this one has to start at 0. That one has to start, well, and we look at it and we see it starts at 1. Curtis.
When cosine is equal, or the cosine question, 1 plus x cosine x is equal to 0, the derivative of the integral is 0.
The derivative?
Yeah.
How do you know that the derivative is 0?
Has no slope.
You mean the integral?
The derivative of the integral.
The derivative of the integral is equal to 0. Interesting. Interesting. Hey, you know what? Beyond the scope of this section, why doesn't everybody graph the derivative of that? See what happens. Derivative is math 8, and then put the integral inside the derivative. Just out of curiosity.
You can just do y2. Or you mean for the derivative?
Yeah, if you wanted, you could also just do y3 is equal to the derivative of y2. And then you don't have to worry about it so much. Yes, and x equals x. But if you're going to do that, then tell it to not graph y2 because we don't want to look at y2. We don't want this to get too confusing. So you can do it either way. You can either just shove the new derivative in or you can make a new equation. What do you notice? Is it still graphing?
Cancels out.
Those of you with color calculators may notice that they do these things faster because they have more memory, more processing power. That's really the difference other than the color. The difference between the 84s and the 84 colors is the amount of processor and memory.
How much is it like this?
Well, let's just put it this way. If you had lived in 1955, the computer required to do the calculations that your graphing computer do would probably take up this whole school campus. And it would probably use the same amount of electricity that is currently needed to power the whole of Seattle. You guys are walking around with computers in your bags that are more powerful than anything known to man in history of computing. And just think, they put people on the moon with that old one.
Yeah, so it's,
What did you discover? Still going?
Dave, how much RAM does this have? Like 256?
So when I was in high school, I want to say I was in the 10th grade, and we went on a tour of the Vancouver International Airport. And they took us to the computing system that ran their flight control computer. It had this much RAM. You ready for it? And it was core. It wasn't microchip. They took a big giant sheet of copper and they put an insulator on top of it, and then they roll it up like a jelly roll. Core memory, that much.
Like you can Bluetooth to another calculator, so you can see what they're doing.
Bluetooth.
Yeah,
I don't
like,
think you can use that as a.
no, like you can write what you.
So guys, did y'all notice that those actually cancel each other out? That's a spoiler alert for down the road. Integral is the opposite of derivative.
Yep.
It is the inverse function, if you want to think of it that way. Take the integral and take the derivative, it'll take you right back where you started. But that's well beyond the scope of what we're doing here and what we're talking about. All right, let's talk about
I erased it.
the integral of -1 to +2 of absolute x over x dx. You'll find absolute in the math number menu.
Graph it, you said?
No, just calculate it.
Oh, okay.
Wow, that took a lot.
Well,
And like definitely involves that.
what'd you get, Teresa?
1.000002.
What'd you get to 3 decimal places, Teresa?
1.00000221.
That's like 9 decimal places.
Well, it's because you asked, you said that the placeholders don't.
That's not a placeholder, that's a number.
Oh, okay, then 1.000.
Those are placeholders.
I thought it
So we-
No.
I know.
No, I did not.
You said that those were placeholders.
Those are placeholders.
Oh, okay.
Because otherwise that would round to 0 if you just said 3 decimal places. And that is clearly not equal to 0.
Well, then that's clearly not equal to 1.
To 3 decimal places, that is equal to 1.
3 decimal places, that's equal to 0.
No.
What? How does that-
Okay. I guess we're taking another side trip. Since you guys won't just believe me, now I have to explain.
I thought, okay.
decimal accuracy. If you have a number followed by a decimal sign, this is your accuracy. 3 significant figures, 4 significant figures, whatever it is. But there is a number right here followed by a decimal sign. 1.000 is equal to 1 within 3 decimal places. 3 decimals of accuracy. 1.000 is equal to 1 within 4 decimal places of accuracy. Okay? That only applies if there's a number here. Now, when you go to this, if you say 3 decimal places, those zeros are there for one purpose and one purpose only, and that's to show you where the decimal is. So 3 decimal places of accuracy is the 2, 3, 4. The zeros are placeholders. They're there to tell you where your decimals start. Okay? There's more to it than this. There's all sorts of different ways to look at it. But if somebody says 3 decimal places, don't round that to 0, because it's not. When you say that something's equal to 0, what you're saying is there's nothing there. Okay? So just sort of keep that in mind moving forward.
I was just confused about how like 0.00 isn't the same as 1.000. Like,
Well, because there's a 1. See what I did there?
yeah.
The algebra thing, what's the difference between 2x and 3x? A 2 and a 3. Yeah. What's the difference between that and that? 1. The difference is that this matters when you're talking about.
That's so weird.
No. No, this is a serious answer. The difference is that when you're talking about accuracy, this is within 3 decimal places of being equal to 1. Okay? When you're talking about accuracy, saying that something's equal to 0, you could. But if you're rounding something to 3 decimal places, you start at the decimal and you don't count zeros unless you're saying it's near 1.
Okay.
So. Don't worry about it. It doesn't matter. It does, I mean, for our purposes, it doesn't matter. No, that's okay. That's okay. That's why I say this is accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places. It's 1 plus or minus 10 decimal places. Whereas the 0, yes, you could say it's approximately equal to 0, but that's not particularly accurate, because when you tell something that something equals 0, you're really telling them that it equals 0. It's about 0, so you're saying, okay, well then there's nothing there. There's the difference. And that's why it's just weird.
Okay.
Don't worry too much about it. Okay, so the area under that curve is 1. What does that curve look like? What does the graph of y equals absolute x? Don't graph it, please. Think about it. What does the graph of y equals absolute x over x look like? What's it equal to? Always? Is it always equal to 1?
So 1 to negative 1.
Except at 0, it's undefined. What happens when x is negative? Really? Yeah, positive divided by a negative. So over here it equals this, agreed?
Yeah.
This is what that graph looks like. And it's actually used, you can just use it to force something to be 1 or negative 1. It's just an easy way to force a graph of y equals 1 or y equals negative 1, depending on which side you're on. So when we're looking at the integral from negative 1 to 2, what's the area of that? What's the area of this?
Negative 1.
Or, as we discussed yesterday, you could argue that the area of that is 1, but that the integral is equal to the area above the curve minus the area below the curve. It doesn't really matter. Depends on how pedantic you want to be. If you want to say you can't have negative area, then you just say, okay, well, then we subtract everything below the curve. Or you just say, oh, what the heck, for all intents and purposes, when we're dealing with integrals, area below the curve is negative. Think about accumulator functions. Anything below the curve, you're taking away. So it's a negative. Doesn't really matter. Either way, that's 2, that's 1. And we get a total area of 1 for that integral. Okay?
There was a decimal. Like what?
So why is there a decimal? Any thoughts?
Because they're doing like the Riemann sign.
Exactly. Your calculator doesn't know what the area of that rectangle is, but your calculator does know that it could split this function into lots and lots and lots and lots and lots and lots and lots of little rectangles and add them all up. But depending on the width of the rectangles, depending on how many rectangles your calculator decides to use, it's going to have to round off delta x because it's only got 9 memory registers. Or maybe 12, I forget. I think it's 9. I'm not 100% sure. It's going to have to round off something somewhere. We didn't have to round off because we know that that rectangle has an area 2 and that rectangle has an area 1. Your calculator's got to have to round off because it's doing lots and lots and lots of little rectangles. All right? How about this one? What'd you get?
5 by 0.
That's what your calculator said? Can't divide by 0? What your calculator said? Why did it say that?
Because 2 is in the domain.
So? What does this function look like? It's what? I can't hear you, gotta speak up.
Not continuous.
Okay, true statement. What does it look like?
It's a line.
It's a line. We don't need to graph it. X squared minus 4 is x plus 2x minus 2. X plus 2x minus 2 divided by x minus 2 is the line x plus 2. So why can't it calculate that? Just because there's a hole right there, why can't it do that calculation? I mean, there's a trapezoid. Is that hole going to affect my area? Why? How big is the hole? How wide is the rectangle right at that hole? When you say really small, how small do you really mean? Yeah. Yeah, that hole is infinitely small. It does not have width. We're missing, I mean, I put a little thing there with my finger, but my finger has finite width. Quite fat, actually, compared to an infinitely small hole. That rectangle right there, too, has no width. It doesn't extend to the left or to the right. So why couldn't I calculate this, but I could calculate this? How come it didn't do the same thing here? How come it didn't say, wait a second, this function is undefined at zero, boom, error, divide by zero? It didn't, but it did there. Why? And on Tuesday,
Oh, gosh.
we'll talk about it. Because it doesn't make sense to me. How come it does it sometimes but not other times? That's weird. It's silly. Don't forget to do the quiz.
Are we like, we were on the side?
Curtis.
Yeah.
You make the kids for
So
the
Penny,
senior.
how could I can.
Huh?
For the senior sign.
Yeah, I did.
They also had white ones and I was like,
Did
Oh, Curtis.
It's spelled it Vincente, but it's VIC. There's no N.
What?
Oh, so it's Vicente, not
Vicente.
Vicente? Vicente.
Oh,
Oh, Curtis, that's so rude.
I didn't hear that.
Hey, you know what? I say from now on, we take the N off of his last name and not have it there.
She spelled, wait, was it you spelled my name wrong for my
No.
birthday board?
Oh, yeah, those are.
Like, she spelled
You
it.
were just getting back at me. Where's my? See, you're just getting. I spelled your name once wrong and you just messes it up.
That's what you get.
Have a great weekend, guys.
Thank you. Where's the okay.
Do a raffle thing. Have a good one. See you Tuesday.
You too. Bye. Bye. You're welcome.
Have a good long weekend.
Oh, yes.
Yep. Didn't even put it on there. That was my partner.
Corbin.
Yep.
So just patch over.
Yes. So now I gotta.
Oh, that was due yesterday.
Yeah, but I can still turn it in today. And mainly, I want to get full points on it because I'm kind of behind in the class.
Hey, you're lucky you don't have teachers as parents.
Hmm?
You're lucky you don't have teachers as parents. But my dad, he's barely parenting.
Dude, you know what's funny? Not really.
Hey. I think it's quite funny. My dad was raised in the Philippines,
Yeah.
so he's white, but he can tell the difference between Chinese, Japanese, and Filipino.
Yeah.
But then he comes here and he's like, all white people look the same. So I'm like, oh, this person looks different. My mom can't tell the difference between Asian people. So it's
Well, yeah.
like,
Okay. So, what's your Okay. So what was I gonna say? I was gonna say something. I can't remember. You played football this year?
no, I just located my right knee.
Oh, I didn't know you did that. Yeah.
This kneecap shifted like 2 inches up and then go back in and I fully extended it. So, yeah.
Fun. Oh my, I wish I could say that. But are you going to college?
Yeah, I'm gonna be ready to start 2010.
Oh, yeah, you see, I'm not going to college, so all I need is my diploma. Like, I don't need anything better than these. Like, right now, all my classes are sitting in. Except for this one, which is incomplete. Which is why I need to get this. 100%.
That's great. It's funny because I never expected me to do it.
Do you want a marker for me?
You're not running it.
Just a close
Can we put it on the bottom?
No,
Why not?
on the back.
I don't know.
Everyone else has it.
Yeah, well, everyone else is ugly. So,
Yeah, but I want it.
no. Sorry.
Good morning, Reading High School. Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. There will be a senior class meeting during P3 today in the auditorium. So seniors, if you are not there, please head down. Attention to all ceramic students from first and second semester. All the work has been fired. This includes any glaze work you may have completed. Please stop by and pick up your finished ceramic work this week. If you still have some glazing to complete, please come into a T3 session or two prior to June 4th, so it can be fired prior to the end of the school year. Thank you. Also, if you not make the meeting, just email Mrs. Heslip or Mrs. Goostetter to vote. And for seniors, we are coming down to the last few weeks of the school. Here from
Actually, we're coming down to the last few weeks of school for everybody, not just seniors, thought I'd point that out.
credit retrieval and complete grade need to be completed and received President Office.
She said for seniors, we're coming down to the last few weeks of school.
Educommittee and online application grades are due in Office.
All right, speak closer, go.
Senior presentations and high school exams.
Did you really do that?
I'm guessing, thinking.
Oh, and are overdue and need to be completed.
Oh, I can shut off this live stream.
If you would like to be a part of this year's talent showcase, submit your videos to Mr.